In this video, we will discuss neural networks. Consider the following non-linearly separable dataset. We will use one dimension for simplicity. Let's look at an example of classification where we overlaid the color over the feature. In the context of neural networks, it's helpful to think of the classification problem as a decision function. Just like a function, when y equals 1, the value is mapped to 1 on the vertical axis. We can represent the function like a box. This box function is an example of a decision function. Any values of x in the following region is 1. Any value of x in this region is mapped to 0. A neural network will approximate this function using learnable parameters. We can also view the problem as trying to approximate the box function using logistic regression. Anything in this region y will be a 1, that is, dog. Anything in this region y will be a 0, that is, cat. If this was our cat-dog dataset, in this example we cannot use a straight line to separate the data. This line can be used to linearly separate some of the data, but some of the data is on the wrong side of the line. We can use the following node to represent the line and the edges to represent the input x and output z. If we apply the logistic function in the context of neural networks, this is called the activation function. These values of the function are incorrect, and we get an incorrect result in this region. We can represent the sigmoid function with the following node, taking the input z from the linear function and producing an output. Technically, a is a function of z and x. We will call the function a the activation function, and the output of a is called the activation. The line can also be used to linearly separate some of the data, but some of the data is on the wrong side of the line. This line looks like it could be used to separate the data, but let's see what happens when we apply the sigmoid function. After applying the sigmoid or activation function, we get an incorrect result for some of the samples. Consider the following sigmoid functions. We call them a subscript 1 and a subscript 2. If we subtract the second sigmoid function from the first sigmoid function, we get something similar to the decision function. We can also apply the following operations with a linear function. That is, just subtract the second activations from the first activation function. These values will be learnable parameters. If we apply a threshold, setting every value less than 0.5 to 0 and greater than 0.5 to 1, we get the exact function we are trying to approximate. We can now classify the data. We obtain the parameters via gradient descent. We can use the graph to represent the process. We apply two linear functions to x and we get two outputs. To each linear function, we apply a sigmoid. We then apply a second linear function to the outputs of the sigmoid. We usually apply another function to the output of this linear function, then apply a threshold. This diagram is used to represent a two-layer neural network. We have the hidden layer. Each linear function and activation is known as an artificial neuron. In this case, the hidden layer has two artificial neurons. The output layer has one artificial neuron. As it has two outputs, the input dimension for this neuron is 2. It's helpful to look at the output components of the activation. The outputs of the activation function is a 2D plane that looks like this. These red data points get mapped to these points in the 2D plane. These blue data points get mapped to these points in the 2D plane, and so on. It turns out that we can split the point using the following plane. This is what the linear function on the second layer does. In the same way, we can add more dimensions to the input. Notice that there are a lot more weights between the input layer and hidden layer. We will leave out the biased terms. We see neural networks have a lot of learnable parameters. For example, a logistic regression model may have hundreds of learnable parameters. A modern neural network will have millions. Generally, these types of neural networks are called free-forward neural networks or fully connected networks, but we will usually refer to them as neural networks. We can use neural networks to classify multiple dimensions. Here we have a non-linearly separable dataset in 2 dimensions. Here we have a neural network with 2 dimensions. The more dimensions, the more neurons we require. We can plot the decision function in 2 dimensions. The horizontal axis is the value y hat. We have cats that are mapped to 0. We have dogs that are mapped to 1. Check out the labs for more.